Now let's take all of our knowledge about hypothesis testing and p-values and let's apply it to a computer output problem. Now in these problems, it's the same idea, except I've done all the heavy calculation work for you and given you the output in a computer program. In this case, I've done StatCrunch below. So a market researcher for AT&T believes that more than 20% of third graders have cell phones. She conducts a study by surveying a random group of third graders, and her results are in the StatCrunch output below. Now you can see what I've already done to this particular output is that I've started labeling stuff, which is a very good idea to do. So I've figured out that X was the count right here, 122, N was 542, P hat I don't know yet. The standard error will be the standard error of P hat, which I also don't know yet. Z0 is my test statistic, and p-value is the one thing I don't have to label because it's already really well labeled for me. All right, so let's figure out what type of test did this researcher perform? Well, this is very much a right-tailed test right here, this one, because it's a greater than symbol. There, I've got that one in. All right, so now we're going to state the null hypothesis in symbols and in words. So the null hypothesis in symbols was rather easy to spot. I mean, it says it right in there, p equals 0.2. Now, what does that mean? That means that 20% of third graders have cell phones. 20% of, let me type it up 1 second. All right, it is assumed that 20% of third graders have cell phones. The alternative to that would be P is greater than 0.2, which is what this lady is trying to prove. So the claim is that more than 20% of third graders have cell phones. There you go. All right, so there's symbols over here and there's words over here. And of course, you'll have to be able to know both because both are going to crop up. All right, now how many third graders did the researcher survey in total? Total, that would be N, which is 542. Right, now how many third graders had cell phones in that group of 542? That's what X is. That's X equals 122. All right, now we're going to calculate P hat. P hat, remember we have a formula for P hat. P hat is X over N, which would be 122 over 542. Oh my goodness, forgot to make my fraction bar there, sorry about that. Over 542. So let me grab a calculator. 0.2251. Okay, so about 0.2251. And technically both of these are correct. It's kind of whichever way you want to think about it. Done with that. Now we're going to calculate the standard error of the sample proportion. Well, this is a little bit complicated, so let me go back and remind you of the formula for this from Chapter 8. Let me go grab those notes. There we go. In Section 8.2, we learned about the central limit theorem for proportions. And you can see down here there's a formula for the standard error of the proportion, which is the SE of P hat, which is sigma P hat, which is the square root of P times 1 minus P over N. Now the problem is that we don't actually know what our population proportion value is. We think that it is our null hypothesis value of 0.2. So let me make a note of that. So note, we do not know the value of P, so we will use P0, which is the null hypothesis value of 0.2. As it is assumed true. We don't know the value of P, but we are going to assume that it's 0.2. So instead of using P here, I'm going to use P0. So 1 minus P0. All right, this is equal to the square root of 0.2 times 1 minus 0.2 over the sample size, which was 542. And that should be approximately something with my calculator. All right, so big square root, 0.2, parentheses, 1 minus 0.2, close the parentheses, divided by 542, 0.017181. And we're going to keep a lot of decimal places there, just for our own benefit, because we learned to keep a lot of decimal places for this. Note, keep 6 decimal places, at least for sigma sub p hat. We learned that back in chapter 8. Matter of fact, if I grab the notes for 8, you'll see right there, keep at least 6 decimal places for standard error. So I'm just trying to keep it consistent here. All right, so now we found the standard error for the sample proportion, or at least our best approximation for it. We are going to find the test statistic and circle it in the output. So let me do that. The test statistic is right here. I'm going to have to give this a different color box, however. I'll make it blue. There we go. So we have a nice blue box right here. That's the test statistic. And since they want the p-value, I'm just going to do the p-value right now because the next question is going to ask about the p-value. And that's this score right here, which I'll shade in green. There we have it. Okay, so I'm going to go type those up. Z0 is the test statistic, and the p-value is obviously the p-value, so there's not much to say about that. All right, there I have those two written down and highlighted appropriately. Now we're supposed to use the computer output to perform step 4 of the p-value method. Draw a graph, shade it, and label it appropriately. So let me bring you back to the picture here of the p-value method. We are doing a right-tailed test. So you're going to draw this right-tailed test right here, just like this. You're going to label your p-value and your z0. Now notice your p-value is actually quite large, so you're not going to give it a really small value. So I drew it. This is actually accurately drawn from a computer program, and you can see that p-value is actually pretty big, all things considered. So you label your p-value, you label your area, nothing should be left out of this. This entire picture is required, right? So you got your p-value, got your 0 in the center, etc. Now, if the researcher set alpha to 0.05, would these results be statistically significant? Well, remember, statistically significant, that little phrase means reject the null hypothesis. Let me type that up real quickly. All right, so remember that statistically significant means you reject the null hypothesis. That's what that stands for. So no, these results would not be statistically significant since we would not reject the null hypothesis because the p-value, which is 0.0721, is not less than, that's what that slash means, not less than your alpha of 0.05. And you want to be less than alpha in order to reject. Remember that we're always interested in low p-values. You always want your probability value to be very low so you can reject your null hypothesis. And we did not have that in this case. So how would we write the conclusion? Well, we would say what we said back in chapter section 10.1. Let me go grab that page. Here it is. So when we talked about making decisions, we would say if you do not reject the null hypothesis, you would say there is not sufficient evidence to support the claim. And the only difference you can change in there is the word sufficient to enough if you so desire. And that's it. And you'll have to write your claim out in English. So right here I would say there is not sufficient evidence to support the claim that, that's all the setup right there. And now I will write what the claim was, that more than 20% of third graders have cell phones. Right? So the beginning part is the setup and the second part is the actual H1 part. And this was earlier from section, so we saw this in section 209. Note, section 10.1. I think it was page 209, but that might change in later semesters, but it's definitely in section 10.1. All right, now suppose that the true proportion of third graders that have cell phones is actually 24%. All right, so we're somehow able to know that in reality, so note in reality, P is equal 0.24 is greater than 0.20, right? So P equals 0.24, which is greater than 0.20. So this is somehow we're magically able to know reality, right? I better put that. So magically, because of course in real life you don't get to know reality, able to know reality, right? So if that's the case and you know somehow, you've got special powers, that P equals 0.24, which is greater than 0.20, what kind of error could that lead to? Well, we need to go back to 10.1 again. So let me grab 10.1. Let's look right here when we introduced type 1 and type 2 errors. So we know that the alternative is actually true. So reality says the alternative is true, right? And that's the real case. We're magically able to know reality. So if that's the case, the only error you can make then is by not rejecting your null hypothesis, which we didn't. So that means that a type 1 error is what's possible. So if you do not reject P equals 0.2, but even though in reality it actually was false, that would be making a type 1 error. So I'm going to go type that up 1 second. All right, so let me see what we said. So remember, by the way, that this past one was the decisions and hypothesis testing box that you want to look for in 10.1. And then this bit is talking about type 1 and type 2 errors. So there's a whole page and a half about that. Actually, there's about 3 pages on that. So suppose you're magically able to know, quote unquote, reality, which is that it's actually 0.24, but that's greater than 0.20. So H1 is really true, right? But we did not reject the null hypothesis, right? And even though the alternative is actually true and the null was false, this means we are making a type 1 error. Type 1 is when you do not reject the null hypothesis and you actually should have because it was false. Whenever you're getting confused on those ones, it really pays to go back to that page that has the box right here and kind of think about, okay, they're saying that H1 is actually true. They're saying that P is greater than 0.20. So the error I'm going to make from that is a type 2. If I do not reject the null hypothesis, which I didn't, then I'm making a type 2 error. All right, and then I think we are all done with that particular example, and we will move on to the next example in the next video. So I'll see you back here then. Yep, right there. And notice, by the way, before I take off, that these two are both hearkening back to those ideas that we had from 10.1, as is this actually, because this is coming from when we learned how to write hypotheses in there and make decisions.